attendance start from today's class until the last class of the semester. So you need to write down your printing name, UFID, and signature. You can only write your own name if you know what I mean. Do not write down names for your friends, roommate, or girlfriend, boyfriend. No, it's not allowed. It happened in my class before, but I figured out. Because this part is not like it is related to your final grade. I know it's bonus part, but it's still related to your final grade. So if somehow you write other people's name, it's considered as cheating. So just want to make it clear. I'm not saying like we will do that, but just want to make clear before we start this attendance. And put on the syllabus. So I will have office hour today after class. So it's in my office, MAEC 106. So you know the building that you had like DML, Mac 3, yeah, same building, 106, right out of class. So I guess 2 to 3. Yeah, I probably need to leave before 3 because I have a meeting in another building at 3. So if you have any question or anything you want to talk to me, please come to my office hour. So let's continue with the content last time. We talk about this. So for this single spring element, we had the elongation is the displacement of second node minus displacement at first node, uj minus ui. It becomes elongation of spring element. And we know that for the element force, which is the internal force, is equal to the spring for the equal to the k times this delta, right? K is the stiffness of that element. And so now, based on what you learn from statics, force equilibrium, we know that to generate tension, we need to apply a force in this way, and the magnetic force, and I know the general, of course, they're the same and should be equal to the internal force of the spring element. So Fi, let's say for generate tension, we need to make sure that force applied node I is in the negative x direction. That's why there's negative sign here. And force applied node J is in the positive x direction. This is how we generate tension. And to generate compression, obviously we need to apply force in this way. So it means that force applied at node I is in the positive x direction, but the force applied node J should be in the negative x direction. That's why we have positive and negative sign here. And for the internal force, we learned this in the mechanics materials. Internal force, whenever it's tension, should be positive. Whenever it's compression, should be negative. So now, based on this basic equation and the sign, we have Fi. Let's start from Fj, because Fj is always same sign as internal force. So now we have Fj equal to P equal to K Uj minus Ui. And Fi is negative, it's always negative of the internal force. So now Fi should be K Ui minus Uj, right? So this is how we got these two equations. And of course, in FEA, we always put everything into the matrix equation form. I wrote on board last time, let's do it again. So it basically, we have the common coefficient 1, negative 1, negative 1, 1. This one and these two equations are the same thing. It's just we wrote in two equations first, and now we wrote in the matrix form. And I also explained in the last class that, well, in the mathematical preliminary, I mentioned that to solve n unknowns, having an equation does not guarantee you have the unique solution, right? The only way that you can guarantee to have a unique solution is that your n equations should be independent equation. But let's check this simple situation. You see this equation and this equation, they're not independent equations. You can just, the first equation, you add a negative sign on both sides, you get a second equation, right? So basically you can say that this is just one equation. So this explains why we cannot have a unique solution for Ui, Uj. And the same thing, let's check this matrix equation form. again, back to what we talked about in the I forgot. Thank you. Yeah. For the superscript, again, this is consistent with textbook, and we will make it consistent for the whole semester. Thank you for reminding me. This E is always the element. The subscript is always the node. So maybe something about like for the UI UJ, we don't say like you put an element here. So this is simply because displacement at each node does not really belong to any element. It's only related to the node, right? So you cannot really say that, okay, let's say if I have different element connected here and element 3 connected here, whatever at UI, no matter how many elements it connected to, UI only belong to that node. It does not relate to like how many elements it's related to, connected to. That's why for the displacement, we only have subscript. It's only about that node. Back to what we talked about this matrix equation form. Again, we talked about we mentioned this in the preliminaries. For a matrix equation, if you have vector with n unknowns, the only way you can get a unique solution is the determinant of this matrix is non-zero. But here, you can see that determinant is 0. It's very easy to calculate for this 2 by 2. So that's also explained in this matrix equation form. We see that, okay, there's really no unique solution for this one. And I also explained in the class at the end of the class last time, well, this is not really a math class. FES is not a math class. It's still a solid mechanics class, advanced solid mechanics class. So the physical meaning of this one is basically when you apply a force during rotation compression, you only know the elongation, but you don't know what is UI and UJ. You only know what is UJ minus UI, right? And let's say if I spring element, I apply tension over compression, let's say elongation UJ minus UI equal to 0.1. Well, I can have this tension applied here, but I can move my spring element to here. So basically, I can have infinite combination as long as UJ minus UI equal to 0.1 satisfy these two equation or this matrix equation form. So this is a rigid body motion in physics, right? So it basically, I can, let's say, this is the origin coordinate, this is x equal to 0. So it means that for this, when I step here, it means this node displacement equal to 0, this node displacement equal to 0.1. But if I move 1 to the right, this becomes 1, this becomes 1.1. So I can only guarantee that UJ minus UI equals 0.1, but I don't have a unique solution. What is UI? What is UJ? So you will see that this kind of property for the K matrix over and over again, no matter what element type we use. But it's okay. So the way to remove this rigid body motion is that we need to apply boundary condition. So an easy way to solve this one is that, let's say this one is basically the spring is floating in the 1D space, right? If I clamped on this side, or of course I can also clamp on the right side, we're done. We have a unique solution. And the way for the matrix equation basically means that, okay, UI equal to 0. We solve for the UJ. We remove the singularity of the matrix. Now this is let's write this one down. In general, this is the element equilibrium equation. So we have K matrix of the element, and Q is the degree freedom vector of that element, equal to the nodal force. Let's put it very clearly. K element stiffness matrix. Q is a vector of element degree freedom. And F E is the vector of nodal force.
You have to get like squiggly lines.
The matrix and a vector. So whenever, we write matrix is bracket, and when you vector, degree freedom is always a vector, force is always a vector. K is always a matrix. Any other question?
Good dimension.
That's a good question. I can spend the whole semester to explain this question to you. Right now for this spring element, since one spring element we have two nodes, left, right, I and J. Each node can only move in one direction, either positive X, negative X. So each node has 1 degree freedom. We have two nodes. So for element, one element, it is 2 by 2 always. Yeah. So it means that K is always 2 by 2 matrix. Q is always a vector of 2 elements, and force is always a vector with 2 elements. But of course, let's say if we have a spring element, a spring system with multiple spring elements, this K matrix we can increase. I can show you soon, like what if we have 2, so you know how to do the assembly. And of course, let's say if you go to the bin, bin for now, but you probably already learned in the mechanics material that for the bin element, you apply a transitive force. It can move upward, so it's displaced in the y direction. It can also rotate, so there's a theta here. So for the bin element, it will have for each node have 2 degree freedom. This may be a little bit different than some of the solid mechanics textbook, because some solid mechanics textbook that have like degree freedom in displacement in x direction, displacement in y direction, and the rotation about the axis. In SA, at least for the textbook we used, this is defined as frame problem. It's not bin. So again, back to your question, it really depends on the type. To talk about like for different element type, how many degree freedom at each node and how many nodes do we have? And so we have the corresponding dimension of the K matrix, dimension of the Q vector, and dimension of the F vector. Any other question?
And the equation.
K is the stiffness of the spring, right? And Ui and Uj, let's say one spring element, this is node I, this is node J. So J represent displacement in X direction. So Ui and Uj is displacement at node I and node J. And F Ej, E is this spring element, and I and J again. It's a force applied at node I of spring element and a force applied node J of spring element. So it's stiffness times degree freedom or displacement equal to force. It's same as what you learned in, I don't know what class, but before you came to this class, Kx equal to F. Yeah. Any other question? Okay. So let's actually write down the property of the stiffening matrix. It is always singular. Or you can say determinant 0 is equivalent. And the physical meaning behind it, let's move it here. if you have any question, you can ask me. Is singular, and the physical meaning is rigid body motion. So of course, rigid body motion means that there's no unique solution for U and UJ, and to remove this rigidity or remove this singularity of the matrix, we need to apply boundary condition, and we can have a unique solution for UI and UJ. So this is for one spring element, but of course, most time you don't have a spring, just ask you to solve one spring element, otherwise there's no need to take FEA. So let's say we have a system with two elements. This is element 1, and at this node, I connect with another element. So we have node 1, node 2, node 3, and spring element 1 and spring element 2. And of course, we have displacement at node 1, we use U1. Displacement at node 2, we use U2 and U3. Stiffness of the spring, or spring constant of the spring, for the first element, K superscript 1, K 2. And for the external applied force applied at node 2 is F2. And node 3, we use F3. And of course, since first node is clamped to the wall, so it's a reaction force, all the reaction force in FEA are considered as unknown force. I know you can solve it for the simple situation, like based on the statics, well, reaction force equal to F2 plus F, but for all the reaction force in our FEA, we consider it's unknown force. We'll show you why we do that later. So now, since we define the node, we define element, we define displacement, and also the K spring constant for each spring element, and also external applied force at node 2 and node 3. So we can use this one directly. We write this one for element 1 and element 2, and then we can put it in one matrix equation to assemble for the whole system. For element 1, let's use different color. We can write as K1, 1, -1, -1. So for all spring element, it's probably the same. It only for different element, you may have different K value, but this 1, -1, 1, -1 is maintained the same for all spring element. You don't need to derive your own homework or exam. You can use directly. So U1, U2 equal to F element 1 to node 1, element 1, node 2. So this is for element 1. And for element 2, we have K2. Same thing, 1, -1, -1, 1. And element 2 is collected into node 2 and node 3. So this vector of degree of freedom becomes U2, U3. And for the nodal force applied for element 2, we have force applied to element 2 at node 2 and a force applied to element 2 and node 3. Right. And now, of course, it's a system consists of 2 elements. So we need to put this one into a big matrix equation. So let's see how to do this. We have, for the whole system, we have 3 nodes. Each node have 1 degree freedom. So after assembly, we should have a matrix equation. The K should be 3 by 3. Make sense? And vector Q should also, it's a vector of 3 components. So we should have a 3 by 3 K matrix. And this system has 3 nodes. Each node has U1, U2, U3. Let's first check how to write this 3 by 3 matrix. We need to combine these 2 into this 1. How to write this 3 by 3 matrix? Anyone? So we simply, well, let's say for the first row, since it's only connected to F1, element 1, so we put this one here, and you should expect that this one, this one times this one equal to this one. And we should put the same component here, right? These 2 should be the same equation. KU1 minus KU2 equal to F1, 1. So what we can do is that K minus, and there's no, you check this one equal to F1, there's no, nothing really related to U3, so the third component should be 0. Sorry, sorry. And same thing for the second row. Now the second row is about node 2. So node 2, we have 2 elements connected with node 2. So we have element 1 connected to node 2. Also, element 2 is also connected to node 2. So now we need to use this equation plus this equation, right? So for the second one, we have negative K1, K1. So this is from this part. And also we have this one, right? So this one, I change the color, equal K2, negative K2. So I got clear about this part. It's basically for the second row, for the first term, we have 2 elements connected to node 2. Element 1 connected to node 2, element 2 connected to node 2. So for this fourth component for node 2, we have node force from element 1, node force 2. And now going back to the element matrix equation, this is node force for element 1 and node 2 is equal to K1, negative K1 UI plus K1 U2. So move to the matrix equation, it becomes this one plus this one equal to this one, or And maybe this is making it more clear. And the blue area is the second. Sorry, here. For this one, it's K2, U2 minus K2, U3 equal to F2 for element 2. So now we put the, we have the second row of the matrix. Any question? Now the third row, what are the three components for the third row?
0, -8.
Thank you. And of course, the fourth component, since node 3, there's only element 2 connected to it. So we only have one term, F2, element 2 at node 3. So this is like the first assembly. That's why I go very detailed from the element matrix equation to the global matrix equation. Now let's move this part, and you can compare these three matrix equation. It should be very clear how we do the assembly. So in the future, you can skip some steps and write this matrix equation directly, because you can see that this matrix is simply you put this one here, and you put this one here. Make sense or not? Or to make it easy for you guys to see, let's K1, negative K1, negative K1, and K1. And for this one, because after assembly, there's really no common coefficient. So K2, negative K2, negative K2, and K2. It is clear? You simply move this one to here, because element 1 is only connected to node 1 and node 2, node 1, node 2. And move this part here, because element 2 only connected to node 2 and node 3. So in your homework, in your exam, as long as you understand the whole process, you can skip this part. You do not have to waste time to always write the element matrix equation. Because let's say if you have a system with 5 elements, you have 5 element matrix equation, then assemble them. It takes a lot of time and a lot of space. Now let's check the force vector, because since the force given here is external applied force at node 2 and node 3. So what's the relation between the F2 and this one? So this one is the meaning of these two components mean that force applied to node 2 from element 1. And this component means force applied by element 2 to element 2. Do you agree that since everything is in equilibrium, all the FEA, all the solid mechanics in undergrad, everything is in equilibrium. So let's say if we do the force equilibrium of this node, does it mean that whatever external applied force applied to node 2 should be equal to the force applied by element 1 to node 2 and the force applied by element 2 to node 2. These two should make sense or not? And same thing here. The given information is always external applied force. So the external applied force at node 3 should be equal to the element nodal force from element 2 to node 3. Because the node should be in equilibrium, right? The force applied on this node in the x direction should be equal to 0. So for this one, I can simply write as external applied force at node 1, node 2, and node 3. And again, F1, since it's a boundary condition, is a reaction force. In FEL, the unknown reaction force. F2 and F3 is we consider normally is given. So if you check this equation, basically, for structure analysis, you normally know what kind of structure you have based on the material property, based on the cross section. So you know the K matrix. For our structure analysis, you also know that what kind of load it need to carry. So that is this force vector of the external applied force is normally given. So we can calculate the displacement response. Make sense? This is a given matrix, this is given vector. We can calculate displacement response. And of course, you guys learned from previous class that for the stress and the strain. Well, strain is a first derivative of displacement. And for the stress and the strain is depend on if it's 1D situation, it's Young's modulus. If 2D, it depends on the Young's modulus Poisson ratio, right? So basically, if you solve for degree of freedom, you solve not just displacement, but also strain and stress and anything more complicated than that. And yeah, so this is how we use FEA to solve the structure problem. So now for this one, in general, we can say that after somebody for a system, it's called a structure matrix equation. Q, S, and F, S. So the KS here is a structural stiffness matrix. It's basically a matrix after assemble all the elements from the system. And QS vector is all degree of freedom of the system. So for our example here, we have 3 nodes. So U1, U2, U3. All degree of freedom of the system. And force is all externally applied force at each node. So now we have the definition of the element matrix equation and structure matrix equation. Of course, you don't need to remember any name or anything, but you need to understand and know how to solve the problem. And also, don't want to confuse you guys. If you read textbook, you may see a little bit difference. In the textbook, I think it defines this one as vector of internal forces. That is not correct. There's some like minor mistake from textbook, which happen to every textbook. But I want to explain here if you see like why the difference from my lecture and textbook. So the textbook say it's internal force, but we need to know that internal force is really the P here. And internal force has its own sign convention. So basically, if it's positive, it should always positive, no matter which point you're considering. If it's compression, you should always, if it's tension, it should always be positive, no matter whatever point you are considering on this spring element. And if it's compression, this element force, internal force, should always be negative. But for this equation, this is the externally applied force. This is the element nodal force. It does not always positive tension, negative compression. this one follow the coordinates. If in the positive x direction is positive, if in the negative x direction negative. So that is the definition here. I want to correct. This is really a vector of the nodal forces. It's not vector of internal force. And the same thing here. After assembly, now this becomes all externally applied force to form a vector. And of course, when we learn later that this force is really a force term in a general term. So it can be force applied in X, applied in Y. It can also be a moment or couple applied. And that couple also considered as a force when we talk about beam problem or frame problem. And now let's check this property of this one. And of course, if we assemble two singular matrix to a bigger matrix, determinant of this one is still 0. So this one is still a singular matrix determinant 0. Oh no, it is. Or determinant equal to 0. This it's not determinant equal to 0. So it's equivalent equal to when we say singular matrix. And for this one to apply boundary condition, how to apply boundary condition for this one? How to remove the singularity of the matrix? Yes. Let's move this to save some time. Don't want to write this part again. Let's move this one. So since the first node is clamped, right, it's fixed to the wall. And of course that we know this part, U1 should always be 0. Now let's put this one at 0. This one equal to 0. And also we know that, well, F2, F2, F3, they are external platforms, they are given. They can help solve the problem, but for F1, we said that reaction force in FA is always unknown reaction force. So basically, we can remove this row. Because if we want to solve for this one, we need given information here, and this one should also, of course, this is stiffness, so this one is always given if we know the structure. But if there any component in this one, in this force vector is unknown, it does not help solving our problem. So what we can do is that we can remove this first row. And also, since we already know that this component equals 0, and remember how we do the matrix vector operation, it's always this one times this one plus this one times this one plus this one times this one equal to the first component, right? And the same thing for this one times U1, this one times U2 plus this one times U3 equal to this one. So now you can see that since this one is 0, actually it doesn't matter what is in the first column, because anything times 0 equal to 0. So in terms of calculation to solve the unknowns, we don't really need anything that multiplied by 0. I need to change. Let's use this color. Now our 3x3 matrix becomes 2x2, and also remove singularity. Now you can check to determine this one. Of course, it's not 0 anymore. We can calculate inverse this one times 2 given information external power force. We can solve for U2, U3. So this is how we apply boundary condition, solve the problem, or remove mathematically is remove the singularity of this matrix. And so it has determinant, it has inverse, and then we can calculate the unknown U2, U3. Makes sense enough? Okay. So let's write it down. How we apply boundary condition. First, we can delete the rows with unknown forces. Unknown reaction forces. And then we can delete the column that multiply with 0 displacement. So now this matrix equation becomes K1 plus K2 negative K2 negative K2 positive K2 and U2 U3. And we have externally applied force at node 2 and externally applied force at node 3. And we can solve for the U2 and U3. So emphasize the foundation part is can really better help you do the software part, because what happened to previous class before is like sometimes they applied boundary condition mistakenly in abacus and somehow they applied force. The whole structure disappeared, fly away. Now you should understand that without proper boundary condition applied in abacus, you cannot really solve the problem. So it's not really like how to use the software, it's really understand the theory behind it. So for this matrix equation after apply boundary condition, we define this one as global matrix equation. Again, you don't need to remember any name of this, like element matrix equation, structure matrix equation, global matrix equation after apply boundary condition. You don't need to remember name, but you need to understand this and know how to solve your problem. So in the test view, you put it simply as K Q equal to F. So now the Q becomes all unknown degree of freedom, because let's say in this example, U1 is given information. We know that U1 equal to 0. That's why we delete that part. So Q becomes all the unknown degree of freedom, and force becomes all the given external applied force, and reaction force becomes unknown. K is the global stiffness matrix. And Q unknown degree of freedom. And F vector becomes no external force. Now, finally, we have the K matrix that is not singular or invertible. or you can say determine non-zero, same thing. And we can solve the problem. Any question about how to apply boundary condition to a structure matrix equation? Anyone? If no question, we have 3 minutes left. We can talk about a example problem in the next class. We will not have class on Monday, right? So I'll see you on Wednesday. We'll continue in the next class. Thank you for coming and have a great weekend.